So far, we have been able to define the derivative of the function f of x in the following terms. That dy by dx is equal to the limit as the increment of x goes to 0 of dy by dx, and we've said that this can be represented as f prime x. Now Leibniz looked at this and saw that this quotient here need not always be a quotient, that this formula doesn't necessarily always have to look at how dy changes with respect to dx. And so he, for the very first time, was able to split this as two individual objects. He basically said that if dy by dx was equal to the first order derivative of x, then dy itself could equal the first order derivative of x times by dx, just a rearrangement of this. Now that makes this object different to that fundamentally. This is called the differential of y. That is the differential of x. Now what does this actually mean? Well, if I had a graph and I had y on here and I had x on there, and then I had a curve such as that, and I had 2 points and they were P and they were Q, two abscissae, then what I would find is that the increment delta x and the increment delta y could be drawn like that. They would be the increments of this curve as I move from P to Q. However, one of the things that we have done here is we have suggested that as delta x goes to 0, then we're basically considering ever smaller and smaller increments. And we eventually discover an increment so small that the relationship between P and Q becomes locally flat. It becomes a straight line, or the tangent at P. And so therefore, what dp represents, not dp, dy or dx in this case, is not the increment as we go along the curve, but the increment as we go along the tangent. Because when we look at it with d's rather than deltas, we're basically saying that we've assumed that it is locally flat between these points. And if it is flat, therefore this increment represents a small change in values along that locally flat line between these 2 points, which is the tangent.